Electrostatics. Problem. Stable equilibrium of charge. A pendulum consisting of a rigid weightless rod of length L and a mass m with a charge negative q attached to its end is suspended at a point O, see figure A. Above the point O at a distance a from it is A, charge big Q. In which case there is stable equilibrium for charge q and mass m. The acceleration of gravity is g. In this problem, the stability of the position of the charge at the bottom of the pendulum is investigated. Usually, such problems can be solved by two main methods. The first method is associated with the analysis of the forces acting in the system. A small deviation from equilibrium is considered for some parameter, and if force is proportional to the deviation and directed in the opposite direction to deviation, the equilibrium is stable. The second method is associated with the analysis of the change in the potential energy of the system. It is clear that the first approximation in the state of equilibrium is equal to zero, the resulting force is equal to zero. And it is necessary to study the second approximation of the smallness of the deviation. If it is positive, the potential energy increases and, therefore, a force arises that tends to return the system to its original state. Most often, the second approach gives a simpler solution, since we do not need to draw diagrams of the forces acting in the system, which can be quite non-trivial. Sometimes, the force method is simpler, for simple systems. Here we will consider both methods, solving the problem using the force method. Let us assume that the charge is slightly displaced from the equilibrium position so that the pendulum rod makes a small angle alpha with the vertical, see figure B. If the resulting total moment of forces acting on the rod tends to return it to its original position, then the lowest position of the pendulum is stable. Let us write the stability condition of the pendulum, keeping in mind that the moment of elastic force T relative to the point O is 0, where AC is approximately equal to a plus L is the distance between the charges negative Q and Q large after the pendulum is deflected by a small angle alpha. X is the arm of the force F of the electrostatic interaction of charges. Since, as can be seen from the figure, X divided by A is approximately equal to L sine alpha divided by a plus L, the stability condition takes the form of Formula 1. This is the condition of stable equilibrium. This was the solution of this problem by the force method. Solution of the problem by the energy method. Let the potential energy of the pendulum at the lower suspension point be 0 at the angle alpha 0. Then the potential energy of the interaction of charges and the total potential energy are equal to expression 1. It is easy to see that at a small deflection angle alpha the total energy is equal to expression 2. At small angles, approximation 3 is true. Let us find the length of the segment AC using the cosine theorem. At small alpha, we have expression 4, then at small alpha the energy is approximately equal to expression 5. We need to find the difference between these energies P alpha and P0, which must be positive for equilibrium stability. Formula 6. The final answer is given by Formula 7, which completely coincides with the solution by the force method. Compare these two methods and choose the more productive one.